In 1960, a Soviet engineer named Yuri Artsutinov published an idea in a Russian newspaper that was so quietly radical that it took the international scientific community roughly a decade to notice it. Artsutinov proposed that instead of burning enormous quantities of chemical propellant to hurl payloads off the surface of the Earth, fighting gravity all the way up, humanity might instead build a structure that extended from the equator all the way to geostationary orbit and beyond. A tether, an elevator, a bridge between the surface of the Earth and the edge of space, along which cargo could travel using electrical power rather than combustion. The idea had been sketched in rougher form by Konstantin Tsiolkovsky in 1895 when he imagined a tower reaching to geostationary orbit after observing the Eiffel Tower in Paris. Artsutinov made it physically precise, and in 1975, the American scientist Jerome Pearson published detailed engineering calculations that established the orbital mechanics in rigorous form. The concept has been refined, debated, and studied intensively by engineers and physicists ever since. It has not been built. The reason it has not been built is a single engineering constraint that comes down to one question. What material do you make the cable from? The answer, if it exists, is carbon nanotubes. And the story of why that answer is simultaneously correct and incomplete is the story of the most ambitious engineering project humanity has ever seriously contemplated. The physics of a space elevator begin at geostationary orbit, an altitude of approximately 35,786 kilometers above the equator, where the orbital period of a satellite exactly matches the rotation period of the Earth beneath it. An object at this altitude, orbiting the Earth, appears stationary relative to the surface. Communications satellites operate here. Weather satellites operate here. It is the altitude at which a cable anchored to the equator would remain taut without any powered station keeping. The principle is the same as a ball on a string being swung in a circle. The outward centrifugal tendency of the rotating mass is balanced by the tension in the string. For a cable extending from Earth's equator to geostationary altitude and beyond, gravity pulls the lower portions inward while the rotation of the Earth creates an outward centrifugal tendency in the upper portions. At geostationary altitude, these balance exactly. Below, the cable hangs in tension toward Earth. Above, it pulls outward toward space. The entire structure remains taut and vertical, anchored at the equator, extending into space. A climber vehicle attached to this cable and powered by electricity could ascend from the surface to geostationary orbit carrying cargo. The energy required is determined purely by physics, lifting the cargo against gravity, minus the energy recovered as the cargo is accelerated to orbital velocity by the rotation of the Earth beneath it. The energy cost per kilogram to geostationary orbit via a space elevator at commercial electricity prices is estimated at roughly $10 to $30. The current cost via rocket, even the most efficient reusable rockets in operation, is measured in thousands of dollars per kilogram to low Earth orbit and far more to geostationary altitude. The economic transformation that a functioning space elevator would produce is not incremental. It would be categorical. The fundamental material problem is this. The cable must support not only the weight of its cargo, but its own weight across more than 36,000 kilometers of length, while sustaining the tension forces that keep it taut against the competing gravitational and centrifugal forces at every point along its length. The relevant material property is specific strength, the ratio of tensile strength to density. A material with high tensile strength but also high density is not necessarily useful for a structure that must hold itself up. Across planetary distances, what matters is how much strength you get per kilogram of material. Steel, the strongest structural material in ordinary engineering use, has a specific strength of approximately 500,000 Newton meters per kilogram. Advanced carbon fiber composites reach perhaps 2 to 3 million Newton meters per kilogram. The theoretical requirement for a space elevator cable has been calculated to be in the range of 7.5 to 150 million Newton meters per kilogram, depending on the taper ratio, how much the cable widens at geostationary altitude relative to its ends, and the desired safety margin. No material that existed before the discovery of carbon nanotubes came remotely close to this requirement. The space elevator was a physically sound concept with no physically available implementation. Carbon nanotubes, cylindrical arrangements of carbon atoms in a hexagonal lattice, first characterized by Sumio Iijima in 1991, changed the calculation. Individual, single-walled carbon nanotubes have a theoretical tensile strength of approximately 100 gigapascals and a density of roughly 1.3 grams per cubic centimeter. This translates to a theoretical specific strength of approximately 77 million newton meters per kilogram, within the range required for a space elevator cable, depending on design parameters. The physics, for the first time in history, did not say no. The gap between a carbon nanotube's individual theoretical properties and a practical cable made from many nanotubes is the central engineering challenge of the space elevator program. Individual carbon nanotubes are nanoscale objects. Their diameter is measured in billionths of a meter. Current manufacturing can produce them in lengths of centimeters at most. The cable needs to be 36,000 kilometers long. Connecting individual nanotubes into a macroscopic fiber requires transfer of mechanical load across the joints between nanotubes, and those inter-nanotube connections are dramatically weaker than the nanotubes themselves. The practical specific strength of bulk carbon nanotube fibers, materials made from many nanotubes bonded together, is currently far below the theoretical value of individual nanotubes. Research groups have achieved bulk fiber-specific strengths of a few million newton meters per kilogram, improving steadily, but still short of the space elevator requirement by roughly an order of magnitude. The progress is real and documented. Researchers at Rice University, at Cambridge, at institutions in Japan and China have been systematically attacking the inter-nanotube bonding problem, studying how to align nanotubes, how to functionalize their surfaces to improve bonding, how to eliminate defects that create stress concentration points. Each advance moves the practical, specific strength closer to the theoretical ceiling. What no researcher can currently say with certainty is whether the required specific strength is achievable in a practical bulk material, or whether the gap between individual nanotube properties and achievable bulk properties is bounded below the requirement by some fundamental physical or chemical constraint. Assuming the material problem is solved, the engineering of the complete space elevator system involves challenges that are significant but more tractable. The anchor point must be located at the equator in international waters. Equatorial land is almost entirely within sovereign territory, and the geopolitical sensitivity of an anchor for the world's most critical transport infrastructure makes a floating ocean platform preferable. This platform would be the largest offshore structure ever built, requiring dynamic positioning systems to maintain its location relative to the cable above and its anchor chain below. The counterweight above geostationary altitude, the mass whose centrifugal tendency keeps the cable taut, could be an asteroid moved into the appropriate orbit, through ion propulsion over several years, or a purpose-built station. Releasing cargo from the counterweight end of the cable would give it sufficient velocity to travel to any point in the inner solar system without additional propulsion. The cable's rotation would serve as a sling. Power delivery to the climber vehicles is solved, in principle, through laser power beaming. Ground-based or platform-based lasers transmit energy to photovoltaic receivers on the climbers. The efficiency of power beaming over tens of thousands of kilometers requires advances in laser technology, but is not physically prohibited. Climbers would ascend slowly relative to the cable's length. A journey from surface to geostationary orbit would take several days, but the energy efficiency advantage over rockets is maintained regardless of journey duration. Space debris is the most operationally challenging ongoing concern. Low Earth orbit contains thousands of trackable debris objects and an estimated millions of smaller fragments, moving at velocities that would sever a cable on contact. The cable could be designed to deflect laterally. A wave propagated along its length could move a section of cable out of the path of a predicted collision, but this requires advance notice of all potential collisions that current tracking systems cannot guarantee for sub-centimeter debris. The International Space Elevator Consortium, the professional organization coordinating space elevator research globally, has maintained that the concept is physically sound and that the material challenge, while substantial, is not obviously unsolvable. Annual conferences continue to produce peer-reviewed research advancing the state of carbon nanotube science, cable architecture design, and ancillary systems engineering. The economic case, at the performance targets the design requires, is overwhelming. A reduction in launch cost by 2 to 3 orders of magnitude would enable solar power satellite construction, making clean energy from space commercially viable. It would enable large-scale space station construction. It would make human missions to Mars economically competitive with major government infrastructure programs. The space elevator is the project that, if it works, changes the boundary condition of everything else. The cable is the constraint. The cable is being worked on. The question is whether the material science will arrive before the need for it becomes critical, and whether the will to fund the work at the required scale will materialize without the crisis of scarcity that has historically been required to motivate civilization-scale investment. The physics is not the obstacle. It never was. The obstacle is a tube of carbon atoms that needs to be, in bulk, a few times stronger than anything currently made.